Good evening, students. In this session, we are going to learn the coupling schemes that are LS and JJ coupling between orbital as well as spin angular momentum in case of an atom. In the previous class, we had studied that the electron orbit, the orientation of an electron orbit is quantized along with its spin, and there is an interaction between spin and orbit of an orbital angular momentum of an atom. The objective of this session is to understand how the interaction takes place between orbital and spin angular momentum. This picture will show you the interaction between orbital and spin angular momentum. After this session, you will be able to understand what are the two possible interactions between orbital and spin angular momentum, and you can calculate the total angular momentum of an atom as a whole and the precession of orbital and spin angular momentum about the resultant vector. The prerequisites for this session are: you should have the knowledge of 7 quantum numbers and interaction between orbital and spin angular momentum, knowledge of addition of vectors, because here orbital and spin angular momentum are going to be added vectorially, and how to use the quantum numbers. Regarding the quantum numbers, we are going to discuss in our next session. So let me continue with this coupling schemes. So coupling schemes. Atom consists of a large number of electrons with different orbital and spin angular momentum. Hence, the coupling scheme is very necessary to obtain the resultant orbit and spin angular momentum of an atom as a whole. Generally, there are two types of coupling schemes. One is LS coupling and the other one is JJ coupling. When these two types of couplings occurs, finally we are going to get a single resultant quantum number, that is J. When this quantum number is subjected to an appropriate selection principle, we get a number of spectral lines. Now let us see the first one, that is LS coupling. So this is a common type of combination which is going to be seen oftenly. Here you can see that there are several L vectors are combined to form the resultant orbital angular momentum L, and several S vectors combined to form a resultant S. In this figure, here we have shown two orbital angular momentum L1 and L2 corresponding to two electrons, and they are found to precess around the resultant orbital angular momentum L. S1 and S2 are the two spin angular momentum which are precessing around their resultant S. The resultant L, further the resultant L and S combine to form the resultant total angular momentum J. So J represents the total angular momentum of an atom as a whole. So here you can see that we are going to add all orbital angular momentum and all spin angular momentum, which will give you the resultant L and resultant S. Finally, adding L plus S, we are going to obtain the total angular momentum of an atom. The total quantum number angular momentum J can take all possible values, that is the positive integral values from L plus S to L minus S, depending upon whether L is greater than S or S is greater than L. It means J can have values from L plus S to L minus S, that is J is equal to L plus S, L plus S minus 1, and so on up to L minus 1, L minus S plus 1 and L minus S. The LS coupling is possible when the interaction between the individual L and S angular momentum is very strong. Otherwise, the JJ coupling is going to be dominated. So this coupling is also called normal coupling or Russell-Saunders coupling. Now we will go for the discussion of JJ coupling. In this scheme, the interaction between the orbital and spin angular momentum in each electron is stronger than that of the individuals. Hence, the contribution to the total angular momentum due to several electrons of the same atom is individual contribution from each electron of the atom. If the total angular momentum of a single electron in a multi-electron atom is J is equal to L plus S, then the total angular momentum of the atom due to several electrons may be written as L L1 plus S1, will give you a J1, the total angular momentum of an electron. L2 plus L2, L2 plus S2 will give you J2. Similarly, up to Ln plus Sn, and finally we are going to add the total angular momentum of each electron as a J1 plus J2 plus J3 up to Jn, which will give you the resultant total angular momentum of an atom. In this type of coupling is experienced very rarely. Here we are going to represent diagrammatically how the LS coupling occurs and the JJ coupling is going to occur. In figure representing LS coupling, you can see that L1 and L2 having two different magnitudes are found to precess about their resultant orbital angular momentum L, and this resultant angular momentum L further it is going to precess around the applied magnetic field B. Similarly, spin angular momentum S1 and S2, they precess around the resultant total spin angular momentum S, which further precesses around the applied magnetic field. The resultant L and S are going to give the total angular momentum of an atom in LS coupling. You can see here in case of the figure representing a JJ coupling, here there is S2 spin angular momentum, S1 spin angular momentum of electron 1 and orbital angular momentum of L1. They independently precess around the resultant total angular momentum J1. Similarly, L2 and S2, the orbital angular momentum and spin angular momentum of another electron, they found to precess around their resultant total angular momentum J2, and further J1 and J2 they found to precess around the applied magnetic field B. So this is how you can see the interaction between orbital and spin angular momentum in case of LS coupling and orbital and spin angular momentum in case of JJ coupling. In this session, the total angular momentum of an atom can be determined with the help of coupling schemes that we came to know here, and there are two possible types of coupling schemes which are generally known as LS coupling and JJ coupling, where in case of LS coupling, the total angular momentum of an atom can be obtained by adding vectorially the resultant orbital and resultant spin angular momentum, and in case of JJ coupling, total angular momentum of an atom can be obtained by adding individually the total angular momentum of an electron, that is J is equal to J1 plus J2 plus J3 up to Jn. Thank you, students.